Sorry for the late. Let me start. So today we will continue with the this reaction mechanism. So this is day 21, and it's the last of this. Is last of this of what we have done. We have seen the square planar complexes, and then we have done with the octahedral complexes. So only this part is left. What is the isomerization reaction? Now this isomerization reaction can take place. I mean, for any octahedral complex, as you can understand, let's say this is a reaction. And how can it be possible to isomerize, let's say A, B, C, D, E, F. So if all of them are this individual ligand, then the possibility is only by bond breaking, right? Because if you have all of them have the same position, I mean, if you rotate it, it will be the same. And if you have chelating ligand, then you have one side bond breaking, one side bond breaking is possible. Now, if you look at this for this isomerization reaction, so today the topic will be a little bit difficult, I mean, a little bit more. So I kept everything, almost everything in the slide, but I shall also explain it to you. So if you remember, there was a term that Berry's pseudo rotation. Berry's pseudo rotation gives you that that what is there is no barrier. I mean, if you just in the vibrational motion only supplies the energy. I mean, the molecule do not need too much of energy in the trigonal bipyramid to the square bipyramidal and all these things. So you don't need too much of energy to change the geometry. So what happens if you have a molecule? Sorry, I could not find this particular example. Okay. So if you find this a molecule, then it is possible that it just without bond breaking, it can form. I mean, then this TBP 2 square bipyramidal. So I told you these things in this when we were discussing this tetrahedral and square planar, this del T value and this del for square planar, all these things, we have discussed that it is possible for some system like nickel 2 that it can between this tetrahedral and square planar, and here it is between the TBP and the this square bipyramid is square pyramid. Now the point is that, so if it is possible, that how it is happening. So this, here one of the equatorial bond is moved to the axial bond. Move to the this equatorial bond move to the axial bond, and here it is, or maybe it is just moving to the another axial, and this one is going to the equatorial bond. So it is possible that, or here what is happening, these changes, I mean, from here also you can do the same thing, and you can see, I mean, if you just draw it like this, it is also possible that it is moving towards this and it is moving towards this. So in this way it is possible. So now what happens, if you have a square, as I told you that if you have cis and trans geometry, if you have cis and trans geometry, then it is possible that in case of cis, no isomerization And in case of trans, isomerization happens. So what happens in trans, if you are moving this ligand from here and the same position another ligand is going, then there is this retention of configuration. Tell them to stop. And if you have this X is removing and now you have this structure. Now, if you do not have any chelating ligand, what are the possibilities? So, if this is one of the position, so if this is the position, you can see that when ligand is moving and coming from this one, then this is the retention of the, so these two are similar, so the retention. And if it is coming from here, then what happens? This bond moves to this position, this position, and you get this one. And if you have, so what we can write, it is one position, we can write this is two position and this is three position. So it is one position, it is two position, and it is three position. So a little bit of problem is there in the so this will come, if this comes from here, then it comes here, and this bond, let me, and in that case, it is going to this side, and for this one, it is going to this side, and for the one position, it remains the same. Thing, if let me play one thing. Let me first show you the picture. So if you have chelate ring, what happens? So chelate ring, this is three chelate ring. So isomerization is possible with bond. And once the molecules rotates, if it inverts, it rotates, and then it can be like this. You can rotate the molecule, and when it comes to join again, it can come through here, and these two are isomers. So this is quite simple. You just single axis, you can rotate it, you can rotate the whole molecule, and then you can join from other side, and you will find that both of them isomer. But the interesting thing is that this Baylor twist and Raeder twist shows that if an octahedral complex with chelating ligand can also isomerizes through different geometry. Like what geometry? What if I have an octahedral? Then we take this double prism type thing, but it can go through the other geometry, like the prism in a different way, and it can show the geometry. So from this picture, you may have some idea. Let me show you this video. I hope the video will. Can you see the video?
Yes, ma'am.
Okay. So now you see there are four structures, right? So the first structure is like this. So what happens? You have this one and you have the chelate from this side and this side. So I think you can understand. And now once you give this one, it has been, so what has been done? It has been inverted a little, maybe, I mean, it is rotated towards your side. So here is the blue, and you can see that there is the blue, a little a change. And then if you just go here, you see it is so what is the difference between these two? Look at these two. Here the blue is there, the red is here, but here the blue is there and red just has inverted. So you are just inverting it, and green is now here. And now if you just do it, so here it was the blue was at this side, and here the blue is at this side. So these are different isomers I mean, now if you just look at this, see the red is exactly at the same position here and here, here and here. You just see the red is at the same position, but here the blue is along this side, here the blue is along this side. So the phase changes. So this is the Riedath and Baylor twist. So you just know it. I mean, it may help during this isomerization process.
Ma'am,
Yes.
ma'am, it is slightly difficult to visualize this like from the video itself. Could you paste the link in the chat box?
Okay. Okay, so my suggestion is that today you just have a look, because we have a more important thing to finish, right? Just you look at it, and if you do not understand, again I shall explain, no problem. Don't worry.
Yes, ma'am.
Right?
Thank you.
Okay. So let us start the this more important thing, because this is quite related, and it will be better for you to understand in one day, and then you can read, and it is a little bit I mean, you have to understand what is happening. So till now we have read the ligand substitution reaction, right? But what about the redox reaction? So this, I mean, along the course, we have learned that for d orbitals, this redox is very important. They can they can change oxidation state, and this is extremely important. So what is the redox reaction? So there are A and B, and one of them is donor, and one of them is, let's say this is the this is S. Okay, A1. Let's say A plus B minus, and then it becomes A plus B. So one of them donates and one of them accept the electron. So this is the, so what happens in this process, the reactions, reactions, substitution reaction, what we have covered till date does not have, there were no change in the metal oxidation state. But once you goes into the redox reaction, you have change in the oxidation number. Now, what could be the mechanism? So the mechanism of this redox reaction has been classified into two very important this category. One is called inner sphere reaction. Inner sphere reaction. And the number two is the outer sphere reaction. Right. So from the two names, you can easily understand that this inner sphere reaction and outer sphere reaction, the electron transition in the inner sphere means if you have A and B, both of them have some relation, or both of them had agreed to transfer the electron from from one of the species to the another among themselves. So they don't want to involve any other species into this to dictate over their reaction rate on all these things. But the reaction rates definitely it depends on the inner property of the reaction, this redox couple, and definitely there is a del G of the reaction is involved, right? So let us see that how can it be possible. So let me in the slides it is written in a so I just want to see the one of the examples. Okay, let me take the example. This is the reaction. So this is the reaction. What is this? Cobalt Cl NH3 whole 5 2 plus chromium H2O whole 6, let's say 2 plus, right? And here the oxidation state of cobalt is 3 and here the oxidation state of chromium is 2. Now the reaction product is cobalt NH3 whole 5 and 1 water maybe here now in the solution, and then it is 3 plus chromium, sorry, 2 plus, because here it was 3 and 2, and chromium 3 is it okay? So here it is from 2 to 3. So this is reduction and this is oxidation. Now, why we are telling it inner sphere? So let me give you the information that this is inner sphere reaction. So very quickly, within 1 minute or within 30 seconds, can you tell me one experiment that confirms that these two species does not involve anything other than themselves in the reaction? So I'm giving you 1 minute. So is there anything that you can that will help us to decide that no, they only interact among themselves for these redox reactions? So quick, just try, look at the reaction and then tell me. So now you can unmute yourselves. Please let me know. Anything what you feel, please let me know. Please let me know anything you. Please, anybody, are you writing in the chat box? No, there is nothing in the chat box. Please tell me. I mean, whatever you feel free to tell me. Are you people in the class? Yes, someone wants to tell something. Please. I do expect that you can answer this question. It is very easy. See, if you have the reaction, what could be the way of the reaction can take place? That CO, Cl, NH3 whole 5, right? 2 plus, and then it can dissociate. So, I mean, you have read it recently that how can substitution take place. So it can happen that this is 3 plus, right? And then there is a Cl minus. Now, if you in the solution as a solvent, within solvent, if you give this 37 chlorine, I mean this isotope leveling, let me write, then what will happen? Then when the chromium is taking the electron, taking the chlorine minus, it can take from solvent or it can take from the whatever chlorine has been given by the cobalt. But it never happens. I mean, if I write this chlorine as this green chlorine, always here you will find this specific chlorine here, and you will never be end up with any side products about the reaction, right? So actually what happens, it is called the inner sphere reaction. And now you, I mean, the first day, what we have, I mean, from the reaction mechanism, first day, we have told you on the name, ideally, this Wilson's, this encounters. So let me show you this one. So this encounter species or precursor complex. So what happens? These two comes closer together. So if we just draw it, we can write this cobalt chlorine part and we write the chromium part, right? And here you have this precursor complex, means they come closer. They come closer, and once they come closer, I mean it is very close, so that they form a bridge complex. Actually, you may not have exactly a bond, but the distance is so that a bond could be formed, and it is written as this. So this is the new bond that is forming, and then you have the successor complex. Cobalt is with H2O, and this water is I mean, as you can see that water is going out of the system. I mean, whatever may be the, here it has kept in yellow, and this is, let us think that this is the water. because, okay, let me show it like this, that at this stage, this water goes out. Whatever is that, whatever chromium is releasing, and then this bonds here and chromium forms with chlorine. So is it okay? And then diffusion apart and the redox reaction is over.
Ma'am, a doubt.
Yes.
How is it decided which ligand forms the bridging complex? Like suppose instead of water we have chlorine and bromine. Suppose then
Yes.
how do we know that?
So you have chlorine and bromine, let's say, then it is not it may not be possible that this reaction will go to the through the inner sphere reaction, right? It might go with the outer sphere reaction. So how do you decide that whether it is a inner sphere reaction on this thing? So if you have like a reaction where you see that one of the there were difference in the ligands. So there is a, what are the points? The ligands are different. So from the precursor complex, the precursor starting complex, if you look at this reaction, then you have different thing. I mean, if it is, let's say water, it is not bromine for that matter right now. And there is a difference between the ligand part of the metal. And if you see that the particular chlorine is replaced here, and the reaction rate is quite high, because as you can see that transfer is going to take place within an inner sphere, and the rate of reaction is quite high, and then you can say this is a inner sphere reaction. So if you have a, let's say what your question was, that if you have in this complex, like in this complex, you have two different molecules, right? This is your question. So
Yes, ma'am. What I wanted to say was suppose like we have C. Could you?
Br and CCl.
Yeah, we have Cl and what we have is that Cl and H2O are getting exchanged, right? For
So see, I mean, if you have this, here you have a chlorine and here you have a, let's say, I mean, no, it is. Okay, please repeat the question. Like you have, this is, let's say this is A complex, okay? This is
yes, ma'am.
A complex and this is B complex, right? So now
Yes.
where will be the chlorine and bromine?
Ma'am, I was talking about the inner sphere thing. Like suppose the blue atom shown there, the blue
No,
one.
you can, yeah, this is the blue atom, right?
Yes,
So,
ma'am.
so this will be chlorine or bromine.
That will be chlorine and the orange one is bromine.
Okay. Okay. See, if orange one is bromine and the blue one is chlorine, then there is no redox reaction. You have to understand.
Oh, yes. But
Right.
okay, right.
So it may happen that, the bromine remains. Only water goes out and then chlorine comes. Then it is inner sphere. This is redox reaction, right?
Ma'am, let's suppose that it's not
Bromine
bromine,
remains.
it's some other atom which will cause a redox reaction. How will we decide what atom will form the bridging complex?
So the whatever is transferring. I mean, if this blue, initially the cobalt atom has this blue atom, whatever may be. I mean, it must have the capability to do the change the oxidation number 1 point, right?
Okay, ma'am.
The second point is, initially, if you find a compound that is the cobalt, this blue one and the other ligand, and after the reaction, you find another metal atom attached to this chlorine, then you can decide that this is the forming the bridge.
Okay, ma'am. So basically,
Okay.
whatever cause, whichever atom is responsible, whichever ligand is responsible for change in the oxidation state, that will form the bridging.
That is very important.
Okay, ma'am. Thank you.
So anybody else has any other point? Okay. Now let me just tell two or three points about this inner sphere reaction. So what are the things? Now, if you look at the reaction, inner sphere reaction, so it is not that all of them are very fast or all of them are same, right? If you take cobalt chromium, if you take rhodium cobalt, whatever combination is that, so this is the it is not possible that all of them have the same reaction rate, but generally for a redox reaction this has uh, quite well fast reaction, so it may have different reaction rate, and in any book you will find that what are the reaction rates of this type of reaction. And now let us understand that what are the factors that actually help you to form the so decide about the reaction rate. So another thing may happen, I mean, here if you have this one electron, like here the oxidation number changes for one equivalent, right? Only one equivalent of change, it is the term is one equivalent. And if you take any reaction where it is two equivalent reaction, means something was in +4 state and another thing is +2 state, and after changing the species A goes to 2 plus and species 2 goes to 4 plus, then it is called two equivalent reaction. And you can easily understand that this two equivalent reaction will be a little slower than the one equivalent reaction. This is one of the things. And also this more labile complex, I mean, here at any point, even if it forms bridging ligand, at any point there is a breakage of this bond, right? Breakage of one metal and one ligand bond, and also here is the breakage of one metal for that metal and that ligand bond. So it is a little bit the rate of the reaction depends a little bit on the lability of this complex, as we have read this lability and I mean what is non-labile and labile complex. So it has a little bit of effect. And also the this I mean there are this only not involving the metal. If you have, let's say, a metal and a ligand, only a ligand is joining, so addition reaction, not only electron transfer between two metal centers. If you have an addition reaction, that is redox addition, I mean addition reaction with the redox chemistry, then also it may form this inert sphere complex. And these things we will encounter in catalysis the most. I mean, let's say one of the solvents, or one of this is not the solvent, let's say this one ligand, let's say only Cl also it can happen that it has a react this maybe 4 coordinated or 6 coordinated, and the another Cl minus is joining to this. So what is happening initially in catalysis? So this M2 plus goes to the, or M3 plus goes to the M2 plus, and whenever they have another acceptor, it again gives the electron. But as you can understand, the intermediate state, when these metal complex is acting as a catalyst, then it is forming, it has to change its oxidation number, and it can carry some moieties to the reaction center, and then also it is possible to have the inner sphere reaction. Now, let us goes to the outer sphere reaction. So I can see that there is the this bridging ligand. It is defined what is the bridging ligand, and then you have this is the rate of this reaction. So it is kept here. And this is again this, as I told you, there's two equivalent processes. Okay, so again, before I go to the outer sphere mechanism, let me again make you understand it, because, okay, I have, this is very interesting. So what is said, that outer sphere reaction says that if you have, let's say, M1, and if you have, let's say, M2, then electron is directly transferred from M1 to M2. Right? So this is the outer sphere reaction, where there is no such bridging thing, and A from electron is going directly to M2. Now, to do such thing, what are the required conditions? This is very important. So this is not a very difficult thing, but you have to very clearly visualize the thing. So how it is happening? It is called that before they do so, they need to reorganize. So what do you mean by reorganize, and who does help in this reorganization? So the reorganize means, if you have a reorganize means mainly this geometrical reorganization through this. I mean, let's say you have a center, I mean, a dipolar thing like this, and you have another thing like this. So these 2 points comes as such that they are facing very close to each other, and electron is moving from this side. Let me do not write this. So electron is going from this side to this side. It is not negative or positive, but I am showing it just to make you understand that this type of reorganization, where they come closer in the geometry so that they can transfer the electron to one of them. Now, if you just do a potential energy thing, then generally it is written in that way. This is the reorganization thing, and here at this point, this potential energy, where they do intersect each other, at that point they are reorganized enough to transfer one electron from one species to another. So this is energetically they are at this point, right? Now the point is that this is one point is reorganization. Number 2 point is electronic requirement. Like, if both of them reorganize at some geometry, will every time they transfer one electron to another, will every time a redox reaction will take place? Yes or no? So, yes or no, every time electron transfer takes place. So, anything between 0 to 1, I mean, if you average out, so this is the probability. So the probability may be 0 or probability may be 1, or if you average that many times they have encountered and that many times they have transferred the electron, so you will have a probability of in between 0 to 1. So do you understand that point? So if you understand these two parameters, then almost the work is done. Now you have some mathematical thing. So please let me know if you understand these 2 points. Another thing, so who actually help in reorganize? This is mainly the solvent. The solvent is very important, and solvent helps these two these species to reorganize. And if you remember, you will face in interview as a chemistry graduate or anywhere that why do you need the solvent to do a reaction? So there are different answers for different reactions. So in case of, let's say, redox reaction, you have this one is very important. And in case of other reaction, you need I mean, let's say you have removed one chlorine for substitution reaction, and the chlorine remain very close to your this metal center, then another substitution cannot come, another substitute cannot come close to that metal center. So this whatever is bond, after bond breaking, whatever product is forming, the solvent is taking and it is helping to diffuse it in the solution. In inner sphere redox reaction also, solvent helps you to diffuse. Solvent does not help you for the reaction, or it is not entering in the reaction, but it is helping in the diffusion. But here, for outer sphere reaction, solvent is one of the main factor who controls the reaction, because geometrical reorganization is very, very important here. And I am giving you one example, and then I shall tell you to think over it. That if you see a reaction, let's say cobalt and this iron and this all these things, we do the reaction in water and the reaction goes very fast, and if you just see that the reaction, it is very easy. But if you just think of a reaction, enzymatic reaction, you know that there are too many enzymatic redox reaction that happens within the this cellular cycle. So if you look at these reactions are extremely slow in some cases, and also because they do not have the solvent. I mean, they have protein structure and all these things. And what we say that you have an active structure and a particular position of that. I mean, metal, if metal is placed in a particular arrangement of that protein, then only it gives you the reaction, and then this is the reorganization that is required for that particular electron transfer. So now you take your time and you tell me whether it is clear to you or not. Because other things you will understand very easily if you understand this part. Is it clear?
Yes, ma'am. It's clear.
Okay. So if this is clear, so now let us go to a mathematical expression. So now we have just 5 minutes time, and I am showing you the mathematical formula for this one. So if possible, again next day I shall again write it. It will be easier for you. So this is the rate equation where you have the electron transfer. It is the nu of n. I'm coming to this all these parameters. And then you have this kappa, and kappa E is the electronic factor. This is the probability of this reaction will take place. And the nu is the frequency. Frequency, how many times they are? Frequency, how many times they are reorganizing? How many times? How frequently? Or you can say how frequently. Right? How frequently they reorganize. They reorganize. Kappa is that probability. It is everything is written, but here you will under probability of electron transfer after reorganization. Now, there are two terms that I have not defined. One is the del, I have not defined, but it is there, del G of transition and this del G of the reaction. So ultimately, as you can understand, for any reaction, del G for this del G reaction, this is the thermodynamic ultimate reaction. Thermodynamics that plays a for this I mean to be the feasibility of the reaction, right? Now this del G transition on which it depends of lambda by 4. So lambda is the reorganization energy. And del G of lambda. Now let us form this picture. Okay, I can show it here. I can draw one picture and can show you. If you understand this, mostly it is so. You have a, sorry. So let me see that this is the product. So this is the product and this is the reactant. So generally, how do we see that this is the del G of the reaction, right? Del reaction of the, I mean, we say this is, and as you can see that to be at par here, this has to go to this a little higher energy from the lowest energy. So this is the transition state. Like here, if you just look at, this is the reaction coordinate, this is the product coordinate. So we write it in there and we say that this is the transition state. Exactly in the similar way, this is the point from where it will come down. So this is the del G star, and this amount is called reorganization energy. Right? And here you can, Marcus reaction I shall tell you in a brief. But here you can see that it is not there. There could be different type of reaction that if you see a reaction where FeH2O whole 6 plus another FeH2O whole 6 and it is 3 plus and it is 2 plus reorganizes to FeH2O whole 6 3 plus plus FeH2O whole 6, 2 plus, then you can see that both of them are in the same position. Let me stop here and let me, I hope you have understand the mechanism, and then it is very easy and we can finish it next day. Yes, Hiranmay has written isotope incorporate, but this I have not seen after that. Okay. So now you tell me that only you assure that whatever is told you have understood, because this outer sphere has many layers, and it can, as you can understand, that you can play between the reorganization energy and the reaction mechanism, and I mean, reorganization energy may be more than the reaction, whatever the del G of the reaction, it can be less, it can be same, and depending on that, the rate of the reaction is depends, I mean, that how fast it will take place. And if it happens that the rate of the del G of the reaction is much less than reorganization energy, then also something happens, very, very interesting happens. So just let me know that you have understood whatever is told. Okay, many people have left the class, probably you have a class, right?